How do you picture a galaxy? Probably as a huge, bright, disc-shaped structure packed with stars. You might also think of a glowing core with a supermassive black hole in the center, a chain of globular clusters orbiting around it, and of course a generous serving of dark matter that keeps everything glued together. And the main ingredient seems obvious: stars, of course, because a galaxy is nothing more than the largest kind of stellar system. But the truth is, it doesn't have to be this way at all. It turns out the universe contains objects with so few stars that they're almost transparent to us, yet still have the sizes, masses, and even shapes of disk galaxies. Or going even further, there are galaxies with no stars at all that quietly, almost invisibly drift through the cosmos. So, do you actually need stars for something to count as a galaxy? In this video, I'll introduce you to a remarkable class of objects that might change the way we think about cosmology, and even the very idea of dark matter itself. No, this video isn't about dark matter, as some of you might have guessed, but the story of dark galaxies begins with it. As you know, when we try to explain the universe on large scales, we simply can't do it without dark matter. This still undetected substance makes up about 85% of the universe's mass and lies at the foundation of galaxies and galaxy clusters. Whatever it is made of on a microscopic level, without its gravitational pull, nothing works. Galaxies don't hold together, and they don't merge into clusters and superclusters to form the cosmic web. And even though nobody yet knows what particles created on the micro scale, scientists have gotten pretty good at understanding it on the macro scale. Observing how dark matter behaves on cosmic scales, astrophysicists describe it as a cold fluid that interacts with normal matter only through gravity. Using these properties in computer simulations, researchers learned how galaxies were born. Shortly after the Big Bang, giant spherical dark matter halos pulled in clouds of hydrogen and helium. These clouds condensed into hundreds of billions of stars, which then gathered into galaxies. And although all of this matches what astronomers see in the sky, there are still a few stubborn problems that aren't easy to explain. For example, the models predict that every giant dark matter halo should also contain hundreds or even thousands of subhalos, smaller chunks that should give rise to much smaller dwarf galaxies. That means any large, massive galaxy should naturally host hundreds or even thousands of dwarf companions. These relatively tiny satellite galaxies can have from hundreds of millions to about 1 billion solar masses and orbit their massive host galaxy. But the problem is that throughout the 1990s and 2000s, once scientists realized all this, they didn't find a large number of Milky Way satellites. They literally discovered only about 10 of them. To put it mildly, that's nowhere near enough if dark matter really works the way we think it does. In the modern era of astronomy, this mismatch has softened a bit. As our telescopes got better, the number of known satellites increased as well. But the problem still isn't fully resolved. This is what we call the missing satellites problem. And it not only pushes astronomers to search more thoroughly for dwarf galaxies, it also forces them to look for possible explanations for what it means if those galaxies simply aren't there. And so, one interesting hypothesis suggests that hundreds of dwarf galaxies are sitting literally right under our noses. We just aren't able to see them, at least not optically. What if most dwarf galaxies simply don't shine because all they have is not stars but only dark matter and the gas it has pulled in? What if there are galaxies that, for reasons unknown, never ignited star formation at all? In the early 2000s, the idea of dark galaxies appeared for the first time, and astronomers immediately began searching for them. As you can imagine, objects that by definition contain no stars, or almost none, must be far too faint to detect with a telescope. So the hunt for dark galaxy candidates begins with searching for large gas clouds, more specifically, clouds of neutral hydrogen. And for that, astronomers have a reliable, time-tested technique, looking for a radio signal known as the 21-centimeter line. This is a natural property of atomic hydrogen. It emits energy exactly at this wavelength. So if you find such a radio signal in space, you've definitely found hydrogen clouds. Next, to separate the true dark galaxy candidates, astronomers compare their radio observations with optical sky surveys. They're looking for hydrogen signals that have no optical counterpart at all. In simple terms, the goal is to find large gas clouds that don't belong to any visible galaxy. However, even after this step, a gas cloud is still just a gas cloud, unless it shows properties expected of galaxies. To be considered a candidate, the cloud has to be on galactic scales, meaning at least a few thousand light-years in diameter. And most importantly, its velocity dispersion or rotation curves must hint at a galactic nature. The cloud must literally rotate in a way that lets us infer the presence of hidden mass. In other words, dark matter. So, here in front of you is the galaxy NG C4254. No, it's not dark, as you can clearly see, but it does have some very interesting features. Astronomers noticed that it looks a lot like a participant in a cosmic collision. The signs are all there. For example, you can see a stream of gas being pulled out of its disk, and one of its spiral arms appears stretched and distorted. The problem is, the second participant in this galactic encounter seems to be nowhere in sight. Researchers ran simulations and concluded that about 100 million years ago, some object with galactic mass must have passed right by it. Since there were no visible companions nearby, astronomers realized they needed to look for dark galaxy candidates. And further searches with the largest radio telescopes indeed revealed a mysterious object full of neutral hydrogen. They named it Virgo H121, and this strange thing lies about 50 million light-years from Earth. It's so large that if it were a normal galaxy, amateur astronomers with good telescopes would easily see it. But visually, that region of the sky looks completely empty. Even the Hubble Space Telescope didn't find any star cluster there. However, the key clue to its true nature was its rotation. By analyzing the Doppler shift of its radio emission, astronomers realized it was rotating far too fast for its gravity to be explained by hydrogen alone. There had to be a huge reservoir of dark matter, roughly 100 times more massive than the gas component. That's actually more than in typical disk galaxies, but totally normal for dwarf galaxies. Of course, once Virgo H121 began attracting attention from astronomers worldwide, criticisms of its dark galaxy status quickly appeared. More detailed radio observations and new simulations suggested that the object might actually be a tidal fragment torn away from NGC 4254. This could have happened if another galaxy, for example NGC 4262, flew past it at high speed. This explanation is reinforced by the fact that similar galactic debris has been found everywhere in that same region of space, the Virgo cluster. The concentration of galaxies there is so high that interactions are extremely common, and they can easily rip pieces off one another. It also turned out that the cloud's dynamics, initially interpreted as rotation, actually fit much better with gas motion in a tidal tail. So the idea that it contains dark matter is now largely dismissed. Still, supporters of its dark nature haven't disappeared. They argue, if the cloud was truly pulled out of a larger galaxy, then why weren't any stars dragged out along with it? Either way, today Virgo H121 is no longer the strong dark galaxy candidate it seemed to be 20 years ago. Some call it just a fragment of a larger galaxy, while others think it may still be a fully independent gravitational object. But this specific case, and many others like it, taught astronomers a valuable lesson for future searches. The ideal dark galaxy candidate must be isolated in space. In other words, the absence of a massive companion makes it much easier to rule out the galactic debris explanation. Only objects that formed on their own can be considered true dark galaxies with confidence. So, in 2024, a group of astronomers from the Green Bank Observatory stumbled upon an intriguing object entirely by accident. The team was scanning the sky with their 100-meter radio telescope, searching for low-surface brightness galaxies, most of which are just dwarf galaxies. During one of their planned observations, the team suddenly realized they had pointed the giant antenna in the wrong direction. But instead of finding nothing, the astronomers ran into a huge object, literally galactic in size, with a significant concentration of hydrogen. After detailed optical observations, the team found no bright or even faint galaxy in that area of the sky, which led them to understand that they had discovered something more than just a gas cloud. It appears that this large patch of neutral hydrogen rotates almost the same way a spiral galaxy does. The amount of gas they measured is roughly 1/10 the mass of the Milky Way. But spread out across a region the size of our galaxy, astronomers aren't giving precise estimates of the dark matter content yet. so the study of this dark galaxy candidate is only gaining momentum. The most fascinating part is that this object, whatever it turns out to be, seems to be isolated. There are no massive neighbors within 330 million light-years. In fact, the Milky Way itself appears to be its closest large companion. Normally, astronomers expected that in such relatively empty regions of space, gas should be far too diffuse to accumulate into anything resembling a galaxy. But it turns out that's not entirely true. Because of that, the authors cautiously suggest that this dark object may have been on its own since the dawn of the universe. It could have existed for billions of years as a standalone giant pocket of gas and dark matter, barely changing over eons. If its status is confirmed, this might be our first glimpse of a truly primordial structure, a primordial galaxy that, for some reason, never ignited star formation. Astronomers still need to check a lot before making any firm conclusions, but the very fact that something this dark and this large has been discovered is incredibly exciting. And by the way, this object isn't unique. In 2023, a group of Chinese astronomers reported the discovery of another isolated dark galaxy candidate just 94 million light-years away. They found it thanks to the giant dish known as FAST, the world's largest single-aperture radio telescope. The object, similar in size to a dwarf galaxy, has a disk shape and also rotates like a disk galaxy. Unlike the previous candidate, here astronomers eventually managed to detect a few faint stars through deep infrared and ultraviolet observations. However, the stellar mass is only about 690,000 solar masses, while the gas mass is around 83 million solar masses. But even that is just a drop in the bucket compared to the galaxy's total mass. Based on its rotation, astronomers calculated that the object is about 5.1 billion times more massive than the Sun, comparable to the Small Magellanic Cloud. So this potential dark galaxy is roughly 98% dark matter, more than in the typical galaxies we're used to seeing in the universe. But let's be honest, the most fascinating question here is this: why, having so much gas, do these objects not burst into star formation? What stops them from lighting up the way the Milky Way and countless other stellar islands did? Yes, that's the million-dollar question, and researchers are still looking for the answer. One possible explanation is the relative isolation of these objects. With no massive galaxies nearby, there are no gravitational disturbances that could compress the gas clouds and trigger their collapse. On top of that, the gas in dark objects is extremely poor in heavy chemical elements. Almost pure hydrogen and helium clouds cool and collapse far worse than metal-rich ones. Another possible reason is simply the low density of the gas. The dark halo doesn't squeeze it enough, and without external triggers, the star formation process never really starts. Of course, there could be many other factors. Astronomers know plenty of different mechanisms that can suppress star formation. So scientists are only beginning to unravel the mysteries of dark galaxies, and there's still a lot to learn about what's happening inside them. Perhaps these objects will become natural laboratories of the early universe, places where, for some reason, nature never turned the lights on. There is also another fascinating type of failed galaxies. Let's call them the older siblings of the dark ones, known as half-dark or ultra-diffuse galaxies. As you've probably already guessed, unlike their almost completely invisible relatives, half-dark galaxies do contain some stars. Yes, you can detect them optically, if you're lucky. But their properties, in my opinion, are even more interesting, and their role in astrophysics might be genuinely crucial. In 2015, the well-known astronomer Peter van Dokkum and his colleagues discovered hundreds of these faint galaxies in the famous Coma cluster. These were diffuse patches of light, comparable in size to the Milky Way but 100 times fainter, as if they contained only 1% of our galaxy's stellar population. Such low brightness can be explained by a serious gas deficit, which is exactly what you'd expect in a dense cluster where massive galaxies constantly siphon gas away from their smaller companions. However, frequent collisions should disrupt not only the gas but the very structure of these galaxies. So, astronomers believe that these half-dark objects are rich in dark matter, which shields them from total destruction. Today, we know about many different ultra-diffuse galaxies with their own quirks and fascinating features. But among them, one stands out as a truly extreme object, a discovery announced quite recently in 2023. The well-known dwarf galaxy researcher Dr. Ignacio Trujillo was examining sky images from the Sloan Digital Sky Survey. By chance, he stumbled upon a faint smudge that looked interesting enough to investigate more thoroughly. Naturally, ultra-diffuse galaxies show up very poorly in wide-field survey photos, so to get a deeper image, and thus more details, Trujillo and his team turned to the Large Telescope in the Canary Islands. And indeed, the smudge turned out not to be an artifact or some mistake, but a real, extraordinarily diffuse object. The galaxy appeared so transparent that you could literally see other galaxies right through it. The most intriguing part is that it's 10 times fainter than typical galaxies of its class, yet 3 times larger and significantly more massive. In other words, it's an ultra-diffuse galaxy, but one that seems to have been inflated to enormous size while remaining almost see-through. An object with such extraordinary characteristics truly captured astronomers' attention, because usually galaxies with this level of brightness are much smaller and much less massive. Trujillo even showed the galaxy's image to his 5-year-old daughter and asked what she saw. She replied that it was just a cloud, nube in Spanish. And so the galaxy Nube, as it's now called, may turn out to be the largest and most massive of its kind, and at the same time the faintest. But that's assuming astronomers confirm its distance, which is currently estimated at about 300 million light-years. Yes, this object's parameter set is highly unusual, but that's not the only thing that makes it one of the most astonishing galaxies known. In fact, understanding the origin of such a structure could have serious implications for science as a whole. As we've discussed, most ultra-diffuse galaxies have been found in dense clusters as interacting systems, but Nube appears to be a free-floating object, with no massive neighbor that could have stripped it of gas and stars. Still, the discovery team considered the possibility that the galaxy really was born inside a large cluster and was later ejected through gravitational interactions. Yet Nube simply doesn't look like such an object. It lacks the extended tidal stellar tails typical of interacting galaxies, and it contains a substantial amount of dark matter, which is uncharacteristic for ultra-diffuse tidal galaxies. So astronomers explored a second possibility. Perhaps Nube is indeed a puffed-up version of a normal dwarf galaxy. Dwarfs can expand significantly when they pass near massive neighbors. During such encounters, some of the dwarf stars lie closer to the massive galaxy and feel its gravitational pull more strongly. These gravitational nudges give the stars, gas, and dark matter additional kinetic energy. The components of the dwarf literally start moving faster and on more elongated orbits. In other words, the material drifts outward from the center, allowing the galaxy to occupy a much larger volume. Naturally, as the radius increases, the galaxy becomes less dense, more diffuse, and may even appear semi-transparent. But does this explanation work for Nube? Since this scenario requires another nearby galaxy, the authors examined UGC 929, located about 1.5 million light-years away. It turned out that the two galaxies are indeed moving away from each other, meaning they were closer in the past. However, neither Nube nor the second galaxy shows any signs of past interaction, so the researchers reject this scenario as well. Thus, astronomers currently have no logical explanation for how such an object could have formed so large, so massive, and with so few stars. And even more than that, within the standard cosmological model, such objects aren't supposed to form at all. The cosmological model in question is known as lambda cold dark matter, and it's within this very cold dark matter that the key to understanding Nube might lie. At least the authors of the discovery considered this possibility. For the past 40 years, the prevailing idea has been that dark matter consists of hypothetical, indeed rather exotic, particles called weakly interacting massive particles, or simply WIMPs. They emerged right after the Big Bang, have substantial mass, and therefore move more slowly than light. They're invisible and can only be detected through their gravitational influence on ordinary matter. And because WIMPs move more slowly than light, this type of dark matter is called cold, not because of temperature, but because of velocity. In computer simulations, cold dark matter reproduces the large-scale structure of the universe quite well. galaxies, clusters, superclusters, and so on. But when modeling smaller-scale structures, things don't work out as nicely. For example, in dwarf galaxies, this type of dark matter should create higher stellar concentrations in the core. That is, the galaxy should have more stars toward the center and fewer with increasing distance. In reality, this is not observed. Many astrophysicists explain this discrepancy by the imperfections of their models, arguing that if we better account for messy processes like shockwaves or magnetic fields, everything might eventually fall into place. However, some theorists believe the problem runs deeper, in the very nature of dark matter. They propose alternative versions of this mysterious substance. For example, there is the hypothetical fuzzy dark matter. Unlike cold dark matter, fuzzy dark matter is made not of massive but of ultra-light particles, again hypothetical, called axions. Axions clump together differently and can reproduce slightly different galactic structures. So the discoverers of Nube decided to test which version of dark matter best fits its characteristics, and it quickly became clear that the WIMP model doesn't work here. Nube's structure matches its predictions even worse than that of typical dwarf galaxies. It doesn't just lack a dense core, its stellar density is almost constant across the entire galaxy. Given its mass, Nube should be far more compact if its dark matter were truly cold. On the other hand, the model involving axions reproduces the galaxy's extended, diffuse shape remarkably well. In other words, if Nube is indeed a real object, and if it turns out not to be unique in the universe, then fuzzy dark matter explains it much better. Of course, this doesn't automatically mean we've approached the true nature of dark matter. It doesn't even guarantee that Nube is a real galaxy. As a reminder, astronomers are still studying it and, in particular, working to determine its exact distance. But the central idea remains. In the absence of laboratory detection of dark matter particles, studying such unusual astrophysical objects may be precisely what brings us closer to understanding its nature. So the list of dark things in the universe has expanded. To dark matter and dark energy, we can now add dark, and even half-dark galaxies. And perhaps, unlike the first two, these ones won't remain cosmic mysteries, but instead may guide us toward understanding what the universe is truly made of.